So good morning, everybody. Thank you for joining us today. And I would like to warmly welcome Nathan Fitzpatrick, who was one of the first employees of Cambridge Quantum Algorithms company, and actually one of the first quantum companies on the quantum scene in the world. And it merged later with Honeywell on the experimental side. And he's now one of the central figures in quantum chemistry in this company, and he'll tell us about a tutorial on digital NISQ Quantum Simulation. So very much looking forward to that.
Thanks very much. Hello. Okay, so this is definitely more on the tutorial end of the spectrum, but I think it's quite nice because you've got a whole day of digital quantum simulation. There's also, the audience here is very broad, I'm speaking to quite a lot of you. So I think some of the experimentalists might appreciate the kind of quite introductory manner of this presentation. And also, by the end of the presentation, there'll be a bit more complicated stuff, so hopefully there's a bit of something for everyone. So yeah, so I work at formerly Cambridge Quantum and now Quantinuum. Whether Cambridge Quantum was the quantum software side, so I've got a particular interest in kind of compilation and implementation of these quantum algorithms primitives at the circuit level. And so this talk is basically going to be a tool, like an introduction to the tools you need in your toolbox to implement some of these digital quantum simulation algorithms. So yeah. So first things first, we do have a quantum computer now. So after yesterday's lecture, hopefully you're all experts on ion traps. But we have essentially this H-series device. It's based out in it's in Boulder in Colorado, so I was just there for a few days before coming in. Basically, it's slightly different to kind of the typical ion crystal ion trap. We essentially have this racetrack configuration, which maybe has 32 qubits. We're upgrading it to 56 at the moment, and we have these kind of 8 measurement gate zones here. And then we shuttle ions around with this racetrack, and then we implement the 1 and 2 qubit gates through kind of the laser, through laser operations, which you learned right yesterday. Okay. So obviously going from kind of the pure quantum optics, atomic physics approach, perspective, now we can kind of go into like a digital quantum simulation approach. So you can kind of see here we've got like one of these 2 gate zones that we saw before. So this is kind of where one of the lasers will hit, and then there's another place where one of the lasers will hit. Then we've got 3 ions. So I should say we use ytterbium as the qubit, and we use barium as the cooling ion. But soon we'll be swapping that over. Okay, so you can see we've got this red, green, and blue ytterbium ions. These are our qubits. And then you can see here on this nice diagram. And then we initialize them in the 0 state with a laser pulse. And then we can implement our Hadamard gates, these 1 qubit gates on the red and the green. And you can see that's just a laser pulse, pew, on those 2. And then now, what's quite important about this architecture is the fact that because we have to shuttle the ions, there's an important movement step here. So you can see we're moving the ions to the gate zone in preparation for them to do the 2 qubit operation. And this is actually what causes the most error in our device, because the ions are essentially they're very far apart. It's only when you move them that takes quite a lot of time in comparison to the operation. So that's where the error builds up. The shuttling is actually the main source of error in our device. The rest of it's quite the error is called very low errors otherwise. So you can see now we have this 2 qubit gates, which is these 2 lasers acting at the same time in this potential well. So to kind of hold them in this gate zone. And then we have another shuttling step. And we swap them over and move into the next gate zone. And then we have another 2 qubit gate, which we then apply. And then what makes our device very, very nice is that we can do mid-circuit measurement quite well. And this is done by kind of fluorescing with the laser. And then, so sighting with the laser and watching for the fluorescence. And you can tell if it's 1 or 0 whether you get a photon being emitted. Okay. So yeah. So you can see that, basically, yeah, I'm just kind of summarizing what I was saying before, is that you have this split and combine kind of idea where you kind of move the ions around, and to hold them in the potential well, you have this, you have to hold them in the potential well to have to operate on them with the laser. And then one thing that's quite nice is that because we're kind of moving the ions around, we don't have these logical swaps which you see in kind of other kind of like lattice-based quantum computers like superconductors, for example. Like we don't actually have to do logical swaps on the qubits, we can actually do physical swaps. We literally move the ion to the qubit it needs to. To the qubit that it needs to do its 2-qubit gate. And now you can see it kind of gives us this all-to-all connectivity. Now there is a caveat here because we have a finite number of gate zones. So the trade-off here is that we have to like have this thing called the ion dance, where we build the program is shuttling movement around the quantum computer to make sure the qubits are in the gate zones. But yeah, so this is kind of one of the nice things. So as a quantum chemist, this makes me very happy because this is kind of a naturally global thing. So we can kind of, the chemistry Hamiltonians are very global interaction, interacting Hamiltonians. So having qubits which can talk to each other across the whole device is pretty nice. So yeah, so the native gate set that we use. So yeah, so we essentially have these single qubit gates, so we have this U1Q, which is basically X and Y rotations, and we have this RZ implementation here. These are just done by lasers. And then we have this 2-qubit entanglement gate, which is just this pi over 4 ZZ gate here. And from this allows us to create any set of gates. So this really allows us to then start thinking about like this digital quantum simulation picture. So I apologize if you've seen this before, but essentially a qubit is essentially can be represented as this kind of block sphere. We have essentially, it can be thought about as kind of a complex vector space where your 0 vector is on the north pole and the 1 vector is on the south pole. And then the information in the qubit is manipulated as kind of a vector around this block sphere. So you're just manipulating information on a single qubit by operations around this sphere. And you have kind of these primitive gates here. So the obvious one is kind of the X gate, which will flip from 0 to 1. And you have all of these other gates, other single qubit gates here, which manipulate either across the equator, etc. And there's also, when you have 2 qubits, you obviously have to have a kind of you have a 2-qubit entanglement gate, and this is obviously represented by a matrix of size 2 to the n, so 2 to the power of 2, so it's 4 by 4. So you can think of quantum computing really as just linear algebra, with the gate operations acting as matrices on a vector. Okay, and you can generalize this to n qubits. Now, this is a refresher, so I apologize to anyone who's kind of very familiar with digital gate-based quantum simulation. But so here, we've got a simple 2-qubit system here. It is the morning, so I thought I'd start nicely. Initializing 0, both of them, and then we can apply an RY gate. Now, an RY gate is this kind of rotation seen here, which we can represent as e to the minus I theta over 2y, and it has this representation. Now you can see that this you can think of it as an input and an output. So you basically got the input coming on the rows, and then the output on the column. So this is the 0 is coming in here. That's this first row, and then the output is cosine plus sine. So you can see here. So that's how I think about these kind of matrix operations: the input and the output of the qubit. And we haven't touched the second qubit here, but you can see now we've got a superposition of cosine theta over 2 plus sine theta over 2 1. Now we can do a 2-qubit entanglement gate. Now this is where things get a bit interesting. Is that you can see now because we have this superposition. This is called a C0 gate, and this will apply. So this will flip this bit on the condition that this qubit is in the one state. So you can see here, we've not flipped this bit here. So the 0 has not changed the second qubit, but the 1 state has changed the second qubit here to 1. And what this means is you can't factorize this into individual qubit contributions, and this basically means it's entangled. So if you can't like represent something as a product state, then you've got entanglement. Basically, that's one of the definitions. Okay. So now the rest of this talk is very general, so I'm not going to focus on a specific Hamiltonian, I'm just going to think about an arbitrary Hamiltonian. So this is a completely arbitrary Hamiltonian that I picked, don't get too stressed about what it's actually doing on the interaction picture. But most Hamiltonians can be represented as a weighted linear combination of Pauli tensor products. So this PA can be x plus y on the qubit 1 and qubit 0. And the interaction on this Hamiltonian term is weighted by this HA. Okay. So here we've got a 2 qubit 1 and this is a 4 qubit 1. And the tensor products are Pauli. Now, this talk is about Hamiltonian simulation. Well, it's about digital Hamiltonian simulation. And essentially, the Hamiltonian can be thought of as a generator of time evolution. So essentially, that means if you exponent, a generator is something that, if once exponentiated, will cause an operation to happen. And essentially, you can see here that when we exponentiate the Hamiltonian, this becomes what's known as the time evolution operator. And it will take state 0 from 0 time to the state of time t. And you can derive this from solving the time-dependent Schrödinger equation, but for all intents and purposes, you can just take this for a given. And we know that this is a unitary operation, right? So this is where we think that it's just a rotation in space, right? Which conserves the norm. And this is a unitary operator, so we can then obviously implement this on a quantum computer because we know all of the qubit operations are unitary. So what's the difference between digital quantum simulation and analog quantum simulation? This is kind of my definition. So I think digital quantum simulation is it takes a state, it's a unitary, you're forming a unitary from a primitive gate set which takes the state from time 0 to time t. And it's not really concerned about the exact evolution through time, it's more just about the end point and the last point. And then you're synthesizing this unitary from a smaller set of gates. Okay, so that's why I would say it's digital quantum simulation. I'm quite happy to be corrected, but I think that's the simplest way to do it. Explain it. So there's I would say these are the big 4 digital quantum simulation algorithms in kind of a fault-tolerant picture. This is obviously quite an intimidating slide, so I wouldn't worry too much. This is from the Wikipedia page for Hamiltonian simulation. But what I'm just trying to show you here is, because this field has been for such a long time in a regime where you can't actually implement these algorithms, it's kind of been in the field of complexity theorists for a long time. So you can see here that you'll read pages of like 50 page-long papers in this area where they're deriving essentially the error required for this Trotter form of their scales is t squared over e, and you can see this is slightly worse than this quantum signal processing algorithm, which you're going to hear about later. And it's very, very complicated to derive these. And they also derive, so this is the gate complexity. So in theory, this requires less gates to implement the same time evolution for the same error. Now, you can also define it in terms of this query complexity. Now, this is kind of a very abstract picture, where you're saying you've got this operation, I apply it X amount of times, and then the error that I receive in my algorithm is dependent on how many times you apply the operation in a very loose definition. Now, I would say that this, even though this may have better scaling, so this may have better scaling than this one, there's a lot of complexity hidden in the implementation here, which is something I personally am kind of fighting against this, because when you try and implement sort of these algorithms of QSP and things like that, which depend on these LCU implementations, they're really, really difficult to implement, and they lead to like very deep circuits and complicated. So I would say that there's a huge amount of work still to be done. Like, if you're going to pick a field to work on, pick a field, try and work on compilation of these Hamiltonian simulation algorithms. So the rest of the talk is basically the tools required to implement these type of these algorithmic primitives. And just a note, so there has been a lot of work on variational digital quantum simulation, where essentially you have parameterized ansatz, where the parameters encode the way the ansatz can be fixed depth, and then the parameters encode the evolution of the algorithm. Now, there's some work in this area which has shown that it can be implemented but it's typically very, very expensive, and the measurement overhead required for these algorithms is very high. Yes?
Sorry, I had a question to the previous slide.
Yeah.
Are the prefactors known?
So I would say the prefacts are dependent on the implementation. So, like, if someone finds a better compilation, that may bring down the prefactor. Now, that can be very, very large and have a significant impact, not in the asymptotic regime.
Okay. And what sort of, in the current implementations that are around, do you know what the prefactors would be for this?
I've implemented them directly at a gate level, so I can give you numerics. But I can talk to you about, I've got slides that are in this, I've got like an experts pack in the slide deck on the GitHub, which has all this information.
Okay.
So I've got some compilation strategies for this later on. Yeah, so I would say the compilation is really important to actually implement these algorithms in the real term. And it's something that isn't thought about enough, in my opinion. And because we've got these tensor network simulators, things that allow us to build larger circuits than we currently have previously, we can start to actually test and implement these algorithms, I think. At least the components. Cool. So yeah. So basically, variation on digital quantum simulation is very difficult. I would probably advise against it, particularly if you're working on an iron trap platform, which is very slow measurement overhead. These purely digital. I would say they're fully quantum implementations are better. So yeah. So I'm basically going to talk about. I'm not going to focus on obviously QSP and things like that, because we've got a lecture on this later, but I will talk about how to implement Trotter. And some of my colleagues have actually implemented this quite successfully on our device. So Trotterization is essentially, the idea is basically you take the exponentiated Hamiltonian, and then you say, let's slice it up into infinitely small slices, and then we take products of the power of the exponentials. And then it's been shown that in the limit of infinitely small slices for a given time, so as n goes to infinity, this exactly replicates the time evolution operator. Okay. So this is great if you've got an infinitely large quantum computer, but typically, and you can see here that the coefficients here are the interaction coefficients HA are multiplied by T over n. Okay. So this is great if you have an infinitely deep quantum computer with an infinitely large number of successful iterations, but in general, we have to work in a discrete n. Okay. So basically, as soon as we start making n finite, then this deviates away from the exact implementation, the exact operator, and this is what is known as Trotter error. Okay. Now, and you can see obviously Trotterization is as you increase in time, because you're doing sequential slicing, Trotterization will increase depth linearly with time. And this is obviously in the general case. There are some clever tricks with fast forwarding things, but we're not going to talk about that today. This is one of the problems with Trotterization, in my opinion, is that you have to do these sequential operations. You can't really parallelize it. I'm not going to talk about that, but yeah, so the error in this implementation basically comes from the fact that this product here is not the same as this, as the product of powers is not the same as the sum of the exponential of powers. And there's a very nice review paper by Suzuki, who talks about this in 2005, I think, where you can it just breaks down the essence of Trotter error for a simple case. So basically, if you take a simple exponentiated operator, sum of operators in this form, and then you do a simple Taylor expansion. So you got your first term, your zero order term, first order term, second order term. You can see obviously you get these products here. So you got your first order terms, second order terms with the kind of quadratic interactions, and you don't go higher than third order fifth iteration. Now you can see when you have a product formula, you obviously have to do this Taylor expansion twice, and then once you multiply them together, you end up with this form, which is the same up to the first order term. That's why when you have soon as you go to the second order, you might see that here, we've got this product here, 2 times AB, whereas here we've got AB plus BA. Now these are operators, right? And operators that have this property of they may not be the same if you act on them once in one order and the second order, and the reverse order. It's called the commutator. So if your commutator is not 0, this and this are not going to be the same. So this is where Trotter error is derived from. Okay. So you can see, so if you had 2 operators that commuted, this and this would be the same, so this would fall down to this. This is kind of why you might hear in trotterization algorithms like commutators being really important. So like you might want to group all your commuting terms together and things like that, because that means that set of commuting terms will be exact. Now you kind of represent the commutator error in this fashion, where you can kind of see that it's a little bit confusing, but I mean you can say that this is different from this because of this extra term, this commutator here, which is kind of the extra bit that is not in here. Okay. Yeah. Oh, sorry about that. You can kind of see. So commutator error is really important for Trotter. Now, in the general case, it's a little bit more complicated because you might have products of many Pauli types, like as I showed you in the example. And in the general first order case, and second order and higher Trotter implementations, essentially what they do is they do clever products which cancel the terms, which cancel terms later and allow for the approximation to be correct up to higher orders, basically. So second order, you might see second order trotterization, things like that. That's just playing with the product so that the terms cancel and the expansion is the same up to higher order. In the general case, so you can see the time slice here directed by T over R, and we have R slices. The error, it's actually very, very complicated to derive the Trotter error exactly, and this was actually only done, I think, in 2001 by this power team of Andrew Childs, Yatsu, and Nathan Weed, and collaborators. And you can, and essentially what they derive these bounds, essentially, where here you have the norm of the exact operator versus the operator norm of the trotterized unitary you're implementing. And they found the bounds are basically dependent on the norm of the commutator instruction. So basically, commutators are really important for Trotter error. There's a summary of this slide in the general case. And then they derive higher order corrections as well. Now, if you're interested, I would read the paper, but I would brace yourself because it's pretty intense. Okay, so now, how do we implement these Pauli gadgets? So these Pauli exponentials. This is my area of expertise, circuit implementations. So this is let's say we're saying the products in these Trotter operators, the trotterized Hamiltonian, the trotterized time division operators made these products of Pauli exponentials here. So how do we implement these at the circuit level? So this is, I'm going to show you, we use this thing called a Pauli gadget, and I'm going to derive this from scratch. And this, I would say, if you take away anything from this lecture, take away this. These are the most useful circuit primitives I've ever used. They turn up everywhere. Okay. Okay, so how do we derive that monster that I showed you on last slide? So essentially, I said this is very useful gadget. So a lot of kind of implementing these circuit primitives is like figuring out a gadget once, remembering it and putting it in your pocket and saving it for later. Like it might not be, if this primitive represents a multi-qubit parity operation, it might not look like it does, but I'll prove to you that it does. What is a single qubit parity operation? Essentially, it's a Z operation which will return 1 if it is a zero state or -1 if it's in the 1 state. Okay, so you can see here if we had a 0 come into Z, it would be 1. If it had 1 come into this state, which is represented by 0, 1, you get a -1 term. Okay. Now this thing is it's a multi-qubit parity operation, and I think this is one of the first primitives derived actually. And essentially I'll prove it to you. So how do you prove that this is a multi-qubit parity operation? So what I would do is I would start with just a single bit string and just flow it through the circuit that you have. So this is a trivial example, but let's say we start with the 0, 0, 0 operation. Now, this is in a zero state. Now this C0's not going to fire because you've got a zero state here, so we remain unchanged. And then we have, again, a zero state. Again, not unchanged. This is quite trivial. And then we have a zero. This Z will then only act with the constant, with the 1, because this is a zero state. And then this is typically called the compute step. And then we have the uncompute step, which is, this will be clearer in a second when I use a non-trivial example. We can see this doesn't change anything, and this doesn't change anything. So essentially we've got, as we expected, we have the parity operation of the three Z's being equal to 1. Now, let's do something a bit more interesting. So here we have 1, 1, 1. Okay, so now we've got this input coming in here with 1. This is going to fire now, and then it's going to flip this bit. Okay, so now we've got 1, 0, 1. Now, and again, this is now 0. This is not going to fire, so this remains unchanged. Now now the Z qubit is in the third qubit is in the 1 state. This is going to return a -1 operation when the Z parity is acted on it. So we've got a -1 parity check here. Okay, and then we can say we have this step, which obviously we remain unchanged because obviously this is now in 0, so that this doesn't fire. And finally, we're uncomputing, going back to the original state by doing this C0 operation on we're firing and flipping this bit. So you can see now the input and the output is the same, but we've multiplied it by this minus coefficient, which is this, if you've got 1, 1, 1, and you think of that acting as a Z, you get -1, Z, -1 equals 1, -1 equals -1. So if you multiply this together, you see that you get the same answer. So and then it will become clear why I'm deriving this for you. But essentially, now we have this multi-qubit Z operation, we can generalize this to any multi-qubit parallel operation. So you can see that, and we do this by this technique called basis changes on each side of the operation. Now, this is a very powerful technique. So essentially, if you're doing a basis change, you're not really changing the information on the qubit, which is rotating the vector space. But you can see here that we are. So now, this is now so the Z qubit is not changing. So qubit 2 is not changing. This is the Z operation up here. Now we change the Y, the 1 with this. This is the Rx 3 pi over 2 is the Y, and then the Rx pi over 2. This will rotate the Z basis into the Y basis. And on the 0 qubit we have 2 Hobart models, and this will change Z into X. Okay, now I will. So I leave this as an exercise, but you should be able to prove that this operation is exactly the same as this operation here. Okay. Now, why are we doing this? It seems like we've just overcomplicated these simple 1 qubit gates. Yeah, we made this horrible entangled mess. So basically, the idea is that if you swap the Z to an RZ, you can get this multi. So this is now on 4 qubits, a little bit more complicated, but you can see here we've got the same central primitive as this multi-qubit Z operation, but now we're using an RZ. So now we've got, instead of a multi-qubit Z operation, we've got a multi-qubit Z rotation. Okay, so this means that you can start to see that we're getting the form of these Pauli exponentials here. And then when we combine this with the basis change, it basically gives us the power to implement any Pauli exponential that we want. Okay. And you can see that the theta here is related to the coefficient by theta over 2. This is a repetition. Yes?
Why are you using a Hadamard to perform the X basis change instead of an RY?
Just because, the Hadamard is an RY for pi over 2. Yeah, that's correct, I think. Yeah. Yeah, you could totally do that if you wanted to. Yeah. Okay, so this is the most useful primitive I've used in my 5 years of working in this area. So yeah. Hello?
Why can't you put a RZ theta on all 4 qubits? So why is this better than doing that?
Because then that would be So if you had the same theta rotation on each one, and then do basis change. Product of matrices. I'd have to work this out pen and paper, but yeah, that's a good question. I'll have to work this out. I mean, the main idea is that you're keeping the exponential power the same here. Okay. You may have just discovered a new compilation technique. I don't know. Yeah. Yeah, I'm not sure. I'll have to think about that. It does seem like a very obvious choice. But I mean, there's definitely use cases for why this is important in later on. So we actually use the fact that this is acting on a single qubit later on in the lecture. Okay, so now we obviously have this Pauli product. We implement this at the circuit level. Okay, so now we've got a single trotter step. Okay, and obviously the trotter step, we know the coefficient of the trotter step is implemented by Tn, T over n, and Ha, which is the Pauli, is the weighting. And then the theta parameter here obviously is related to the coefficient by this form. And you can see that here we've got this Pauli product Zx, x. Oh, I think that should be a y. Sorry about that. My bad. And then here we've got the Z interaction here. Okay. And you can see they're just represented as the sequential Pauli gadgets which have these CNOT ladders. And this is obviously one of the drawbacks of trotterization, is that you end up with this, like, you have obviously these very sequential operations. So finding ways to parallelize this is one of the ways to improve trotterization. So obviously now you have this gate, this trotter step, we can implement this k times, basically. And you end up with this very deep circuits as you go, because trotterization quite linearly with them. Hello.
Yeah, so one way to keep the trotter step at the most efficient way to integrate with that.
So it depends. I think it depends on the state, on that system of interest. So you'll see later on my colleagues use an Icing Hamiltonian, and that has a very nice form which has like a stacking, very efficient stacking of these Pauli gadgets. Yeah, you'll see later on. But yeah, well, I'll come on to later why this is bad. So yeah, to answer your question. So when we have a Hamiltonian which has quite nearest neighbor interaction, such as this Icing model here, where we have the Z interaction weighted by the J, and then the X interaction weighted by H. You can see that because you have these nearest neighbor interactions, and obviously we're looping over because this is periodic Brownian conditions, you can kind of see that because this is just two qubit interactions, which are nearest neighbor, the ZZ terms here can all be grouped in layers very efficiently like this. Okay, so you get these very parallel two qubit operations for the Icing model, which is very nice. And then obviously, because this is just a single qubit gate here, you can implement this as a rotation, single qubit rotation. But you still have to implement this. You still have to implement this n times, but you can see because the Hamiltonian is quite local, we end up with a very compact full block trotterization. There's not like, you can think about it as like a Tetris game, for example. Like this leads to very good Tetris stacking. And what my colleagues did essentially, they implemented trotterization. They started in the Hobart state on each qubit, and they measured in the x basis. So the initial state was here, with this. It was Hobart state, the plus state, on 32 qubits. They used no error mitigation, which is a sign of kind of how good the device is. And you can see, because we're measuring the x basis here, we're starting at 1. And then we are, as we were evolving in time, basically. So you can see they managed to replicate the exact evolution fairly well up to quite large times here. And you can see that as we go further in time, the trotter error increases. So you're kind of getting, obviously, like you're losing the exact evolution. And now, the difference between the yellow and the green slides here, the lines here, is essentially if we go all the way back So yeah, they essentially the yellow line is essentially doing 2-qubit interaction with its native. It's decomposing the RZ into kind of the ZZ and the single qubit rotations. I think combine these two. Now, some of the engineers worked very hard on this algorithm. They managed to essentially build a new gate which natively implements the parameterized RZ interaction. And that obviously reduced the depth significantly. So yeah.
So coming back to the old question about applying RZ gates to each of the qubits, is that because can it be that we're trying to minimize the number of variation of parameters for them?
So this is a non-variational algorithm. Yeah, I mean, so we're not varying it, but if you've got less rotational gates, then you're going to introduce less error into your algorithm. Yeah. So
would that be one of the reasons why we're not using RZ gates? Rotation
possibly, yeah. Yeah, I mean, I think there have been implementations of these with these multi-qubit RZs with various RZs there. But yeah, I think it's still fairly. This compilation ends up being quite similar. Okay. So so essentially what they did here is they increased the trotter step size until by increasing from one step to the next step, the expectation value didn't change by less than the shot noise essentially. So you can see here basically that small number of trotter steps, this low time requires low number of trotter steps to get a very accurate evolution. Obviously, as we're going further in time, we need to have more trotter steps to get kind of a good evolution. Yeah. And essentially, even though this is kind of the max depth here, so even though these are very shallow, logically these are very shallow circuits, like this is depth 4, right? But because we obviously have these local gate zones, we can't actively implement the logical circuits like in the same kind of time. So we need to actually schedule the 2-qubit gates to act in to be shuttled into these gate zones. So that means that the actual max 2-qubit depth was 8 at 80 for these 2-qubit rounds, which is still quite impressive, I think, for a 32-qubit experiment with no error mitigation. And then this slide is basically, they did cheat a little bit, I'm not going to lie, because they used the fact that you could exactly simulate the results of this, and they're comparing the result they got with the exact Cancellation simulator from, I think, tensor network simulation. But you can see it's still doing pretty good until we get up to here, where this is where they cut off the threshold in the expectation value measurement. They probably could have gone deeper. I mean, some of my colleagues have reported like 800 depth circuits with error mitigation, of like all gates. Error detection, I should say. We don't do a huge amount of error mitigation just because our gates are so good. Basically, we tend to try and implement primitives that use these detection protocols that expire by quantum error correction. Okay, so this goes back to my point where, so if we've got these local Hamiltonians, you can see the gates here stack very efficiently, right? So you can get a very shallow totalization. So you often hear people saying that local Hamiltonians are very well suited for totalization. This is why, because you can basically get very efficient stacking. Now, when you have this is a full body interaction, you typically, well, firstly, this is going to be less easy to stack because it's acting over more per qubit. And typically, when you have full body interactions, you have more interactions as well. So that leads to deeper circuits anyway in totalization. And totalization is typically not that well suited for kind of more complicated interacting systems such as quantum chemistry. Now, I'm biased, but quantum chemistry is the best Hamiltonian, but it's also the most difficult. So that's why there's lots of the complexity results show that kind of trotter for non-local Hamiltonians is perhaps not the best way. Although in practice, I would kind of argue against that due to this prefactor discussion we had before. Yes. Okay. I'll go a little bit further before we stop. Okay, so I'm briefly going to speak a bit about phase estimation, and then the canonical form of phase estimation, and then also kind of some newer NISQ forms of phase estimation. Now, why is phase estimation related to quantum simulation? Well, phase estimation is essentially an application of time evolution. It can be one of the applications of phase estimation is to extract the eigenphase from the Hamiltonian. So you can see here with phase estimation, when you have the Hamiltonian, any unitary operator, for example, when you have the time evolution and any unitary operator, when it acts on one of its eigenvectors, it will produce an eigenphase in this kind of eigenvalue equation here. So this is one eigenvector here represented by psi j. Okay. So basically, phase estimation is exploiting this property, right? You're using time evolution to exploit the fact that you can extract the eigenvalues from it. Okay. Now, I think it's really instructive to think about phase estimation from a very physical perspective. I'm not a computer scientist. I'm a chemist. So I like to think about dynamics, like actual states evolving. And I really like to think about phase estimation in terms of this like complex exponential spiral propagating forward in time. Okay, so you can see here that if we are acting, so now this is a transition matrix element. Yeah, so what I mean by that is you've got one state propagating time into another state. But when we're acting in the eigenbasis, essentially you can pull out this axe obviously here, and we get this nice this complex eigenphase coming out. Basically, when you think about this in kind of the physical picture, as I call it, you can kind of see that there's only one exponential like spiral happening when you're acting on one eigenstate. Basically, so you can see here you've got the perfect spiral, and the gap between the spirals is essentially I think it's e to the jt. I have to check that. But yeah, so the eigenphase is basically related to the gap between the spirals. Okay. It's a really instructive way to think about phase estimation, I think. Now, you can kind of see when you have Trotz error, when you think about things in this picture, Trotz error dampens the signal quite significantly. So you can see here we've got the exact evolution, and the Trotz error is basically ruining the evolution. But interestingly, the phase stays quite in time, but the peaks are obviously dampened significantly in the Trottization picture. And yeah, I should say on the axes, I apologize. So you have time, and then you have the complex result of this matrix element, and the real result of the matrix element here. And you can do this in NumPy really easily and test these things. And I've got some nice code that I've put in the GitHub for you to play with this. Yes.
So by dampened signal, do you mean that the tail distributions become thicker? Or what do you mean by
well, you can see that the transition matrix element is kind of decaying to half. So you end up with basically just a mixed state, right? Yeah. So that makes sense because at the center of the circle there's an equal superposition.
Sorry, I guess I'm saying when you're reading out the ancilla.
Yeah.
Are you saying that the tail distributions of non-correct binary strings becomes thicker, or like
yeah.
what's the measure?
Well. Let me think about this. I guess, yeah, the answer that readout would be different because you're getting a different expectation value here, right? I actually derived the Hobart Model test later on, and I actually use the Hobart Model test to derive these things. But yeah, I mean, if we were to do this, this is all so far. This is all just kind of just linear algebra. There's no quantum circuits here yet. I'm just trying to show you like what's actually happening when you have these propagations in time. We will derive some quantum circuits to implement this. But I think it's interesting that you get this damped evolution to kind of a very to the kind of the 0.5 on both. That's zero. Yeah, zero on both. But the phase stays the same. So the actual phase information, even though it's damped in Trottization, be extracted. Oh, sorry, yes.
Physically, can you please go over why do we have this damping?
Physically, interesting. So, I mean, it's coming from the Trotz error. So the fact that your evolution is now not doing the correct evolution. I think this might be system dependent. I'm not sure. I haven't tested this for other systems. But yeah, I mean, if you want to investigate this in the GitHub repository, that would be very interesting. I don't know what the physical interpretation is damping. All I know is that this is a manifestation of the Trotz error affecting the transition matrix element. Okay. Cool. Yeah, and then obviously when you've got a frequency like this kind of when you've got this complex function, you can always take a Fourier transform of it to extract the frequency. So you can see here, this is just for a single. This is kind of a perfect. This is a perfect eigenstate. So this is like very similar to this picture. Yes, so just one frequency, perfect spiral, and you can see that obviously it's peaking at 1 because we only have one state here. So this will obviously this is normalized. This will go to 1, and then the peak happens when the eigenvalue and so this goes to e to the 0, which goes to 1 when the eigenvalue is equal to the x-axis, basically. Yeah, and this is a simple example of LIH that we did. Now, when you start in reality, you're never going to be able to implement the perfect eigenstates to act on, to propagate in time, right? So typically you have a linear combination of eigenstates, and that's what the psi represents. Okay, and each eigenstate is weighted by c. It's weighted by Cj here. Sorry, that's a mistake. That should be I. Yeah, but yeah. But it should be J. I apologize. So you can see now when we're propagating on this linear combination of eigenstates, what happens is that we get basically due to orthogonality, the off-diagonal terms cancel, but we end up with a linear combination of kind of spirals weighted by their amplitude coefficient. Okay, and how this manifests basically is you've got loads of competing spirals in this kind of dynamical picture, and you end up with this kind of mess, basically. Yeah. Yeah. So you can see, just to clarify, so you can see that this is c squared because we've also got two the Braun ket here, and then obviously for each exponent, for each eigenstate the axle, the off diagonals cancel, and then we get an eigenphase for each eigenvalue corresponding to each eigenvector. Now, yeah, this is typically what you see in real life because state preparation is a very difficult problem, and there's lots of open questions with respect to phase estimation and state preparation. I'm not going to go into those, but yeah. So this is basically the information you're trying to. This is the picture that you're trying to extract information from when you do phase estimation. And it's really a dynamical thing that comes from simulation. Okay, I'm going to have a little 5-minute break now because this is 2 hours. So yeah, if anyone wants to ask any questions, please let me know.
Possibly I missed this, but you had a slide showing the number of trolley steps as a function of evolution time. So I was wondering why the number of trolley steps did not increase monotonically.
Yeah. I asked my colleagues about this, and they said it's some property of error cancellation. Obviously, don't know yet. So it's just one like that. I would say that because it's a periodic function, there's probably as you detrotter, there's probably some cancellation happening to the cyclic nature of the function.
Something specific to this, like Hamiltonian and this decomposition.
I think it's probably. I mean, I think this picture probably happens with all systems. I think there's probably some periodic cancellation error happens. Not many people have really studied this in an experimental picture, so no one really has a good answer. But I would say that this type of behavior is probably commonplace in population. Yeah.
Actually, factorization is something like a float memory space. And float gate usually takes factorization step very short, so it's like if I make the frequency really high, then you'll start into like you may have it if effective Hamiltonian for reasonable state. So like I'm guessing for the last slide you just showed, is there a regime where damping is really small?
When you have infinite number of steps.
Yeah, but if I like factorize with very high frequency, in the Hamiltonian, that's like there's a predetermined regime there. There's Hamiltonian that behave like effective Hamiltonian. While because Hamiltonian behave like effective Hamiltonian, all the eigens. If you're thinking of a superposition of all these things, like have a less tempo or long time after the long time, just like that.
Yeah.
But I'm not sure.
I would be interested to see you expand the calculation in terms of the flow cake picture. That would be cool. Maybe do that in the exercise. Yeah. I actually don't. Yeah, I think it would be interesting to do. I think this is an open question, like what's going on with this damping. So, yeah, that'd be a nice piece right there, I don't know. Yes. Sure, go ahead. I'm not an experimentalist, so I'll do my best to answer the question.
But I'm just wondering, for a given number of qubits registered, how many swaps do you want to type in?
Okay. So basically to do this operation, how much transport is needed? Is that kind of your question?
My question is actually, I think the motivation of the swapping, is it because of the reordering of the terbium characters?
So this is the reordering is. I mean, the swapping is due to the fact that we only have a finite number of zones to do the operation. Okay.
But with the two lines, like for each pair, does the order of the terbium
I don't know the answer to that question. I would assume that they need to be. There has to be ytterbium barium to get the cooling effect. But yeah, maybe ask Professor Monroe this question. I think he's one of basically most of the postdocs and scientists that work with us works with Chris pretty much. So we thank him for all of this his hard work, basically. Yeah. Yep.
What is the dependence on maximum depth against like number of qubits?
What do you define as maximum depth? What's the criteria there?
The dependence of maximum depth and the number of qubits.
So like what's the maximum depth we can get to have to be able to extract some meaningful information from an expectation?
Yeah, so like you show like A in the 32 qubit system. I'm just wondering, like for a smaller system, are you able to get deeper?
Oh, I see. Yeah. No, the depth is the same depending on the system. Yeah. So the max depth we can go to on the H2 device, even if you're on 2 qubits, will be the same as if you go 3 qubits. Although, that being said, perhaps actually that might not be correct, because obviously you have to, when you have more qubits, you have to do more shuttling, and there's obviously like it's a combinatorial problem, right? So then you're going to have more time waiting. So you're going to introduce more memory error. So I actually changed the answer to my question. I think more qubits leads to a more complicated ion dance, which leads to more idling, and then that can obviously introduce more error. So more qubits probably means less depth, but not by a huge amount. It's just yeah. We call this memory error basically. It's the time waiting to do an operation. Let's give it another 2 minutes.
show me the link to your slides again?
Oh yeah, sorry. Yeah, so to answer the question about the prefacts on this page, yeah, so there's a slide, there's a figure in the slides where for the Hobart model, for the chemistry Hamiltonian, we showed like factor of 100 decrease by changing the compilation strategy. Yeah, compilation is a very understudied area of quantum computing, I think. I'm obviously biased because I work at a quantum software company with a compiler, but sorry, yes, let me get back. There you go. Yeah, so there'll be some a lot of these plots that I've shown you now, some of the figures to do that, so that some of the scripts to do that are in the GitHub repo. Most of them are SciPy. Basically, I want you to implement them at the circuit level, basically. So we can use the SciPy implementation as a guide and then implement them at the circuit level. So we've got kind of PyTicket, which is like our compiler. You can compare it to Qiskit if you want, but there's a few things that make it a bit different, such as like this abstraction that we can do with search boxes and things like that. So yeah, so I encourage, there's a little tutorial that has used PyTicket, and there's obviously some of these examples I'm showing in the slides there as well. Okay, I'll move on. So, okay, all right, so canonical phase estimation. So in the slides, I do have a derivation of the quantum Fourier transform. I'm not going to explain it because it's actually quite complicated, but I think for the purpose of this talk, to really understand the canonical phase estimation, you really have to really understand the quantum Fourier transform. And what the quantum Fourier transform, inverse quantum Fourier transform does, is it basically, if you can get your state into this form where you have powers of some phase or acting on each qubit, it will then map you to the basis which to a basis which contains the information about your phase in the fixed point binary representation. Okay, so basically the inverse quantum Fourier transform basically takes you from this power of exponentials representation acting on the ones, and then maps you into bit basis, which is a fixed point binary representation. I was very confused when I saw fixed point binary representation because I had never studied it before as a quantum chemist. But it's quite simple. It's basically a way of representing decimals in binary format, and it's quite confusingly written in this form. But I think with a nice example, it's quite easy to understand. So you obviously got. So we have basically we have qubit 1, qubit 1, qubit 2, qubit 3. Qubit 1 is 2 to the minus 1. So this basically cuts the decimal by 2 to the by a half, basically. Okay, so if it's 1, if the first qubit is 1, it will be a half. It's 2 to the power minus 1. And the second qubit, if it's 1, it will be 2 to the power of minus 2, which is equal. So you can see this is adding a quarter to the decimal. If the third qubit is 0, it has the power to add an 8, because it's 2 to the power of minus 3. But because it's 0, we don't add it to the system, add to the decimal. And obviously this is a 4 qubit representation. So the fourth qubit is 2 to the minus 4, which is a 16, and because this is 1, we add that to the decimal. So you can kind of see here. So the xk basically is the bit readout, and then 2 to the minus k is the amount that the resolution of the fixed point binary representation that you add. So that's what this represents basically. It's a binary fixed point binary representation of decimal. Okay. And the decimals are like half, quarter, 8, and you can just slice up into smaller pieces. So yeah, I know it's supposed to be a NISQ talk, but I think we're going to talk about some NISQ phase estimation algorithms today. But it's instructed to the real one, the canonical one done by Peter Shaw, and I think it was Peter Shaw in the early days. So you have to basically to get into this state, which we can now exploit the inverse quantum Fourier transform to then get our information out, to get these phases out. We obviously have to like do some trickery to get this form. How do we do that? So this is kind of the, I'm sure you've all seen this before. This is the classic phase kickback here. Yeah. So you can see here. So if we're acting on an eigenstate on our qubit, on our second, well, this can be a register, whatever. Our unitary operator which acts on a register which is in an eigenbasis of U, an eigenstate of U. You can obviously, because this is a controlled unitary, the one is only the unitary is only acting on the one state of a superposition, and it's not acting on the zero state of a superposition. Now, because this is an eigenstate and this is unitary, this U can be pulled into here, and we can get this phase here, basically. And there's this kind of spooky property that you can factorize the phase kickback into separate qubits. So yeah, so we try and exploit these controlled unitaries, basically, to get into this form that we can then extract the information with an inverse quantum Fourier transform. And then to get these powers of the phase that we store that are required by the inverse quantum Fourier transform, we can just do powers of our unitary. So you kind of see where this is going. So here's a simple example of a phase estimation algorithm. So we typically do a Hadamard. We have basically this is our bit register. This is our resolution register. The more qubits we have here, the more resolution we get in our fixed point binary representation. So we do a Hadamard in each one of these, and we get this. We get this nice superposition over 1 over plus superposition over 1 over square root of 2. And then what we do is we just do a control, and this is some, in the ideal case, this is an eigenstate of our unitary that we're implementing. Now, we essentially apply the powers of our unitary, control powers of our unitary. You can see we're selectively now applying the powers of the phase kickback to the one state here. This is a one control unitary. So you can see what we're doing now. We're just basically we're preparing the input for the inverse quantum Fourier transform for these controlled unitaries. Okay, and then once we have it in this state, we can extract it through that into the bit basis with the fixed point binary representation. Okay. Now we can obviously apply this to simulation is really important in this area. Okay, so we can then that controlled unitary can be the control time evolution operator, and then we can use that to kind of get the eigenvalues as our we can extract the eigenvalues in the same way. So here's an example. So same as before, Hadamards in all of them, and now we do these controlled unitaries here, controlled time evolution operators to the various powers. And you can see here we've got there should be a T here. I apologize. Whoops. Yes, there should be ET. No, sorry, but no. Yes. Yeah, there should be a T on this one. I apologize. Yeah, so you can see we've got these powers of these eigenphases coming out now, and we could just extract it again with the inverse quantum Fourier transform. And then, yeah, I think it should be ET rather than E. I apologize. Yeah, but the problem is how do we apply these controlled unitaries? Okay, so you might see this in a textbook, and this is kind of one of the big problems I have with the field is that people just label controlled oracles, things like that, and implementing these is really complicated, and there needs to be a lot more research into it. So this is kind of going back to the Pauli gadget that we saw before. If you notice, the Pauli gadget has this thing called got a similarity transform structure. Okay, and this essentially means you have this G, which is a rotation, and you have a unitary operation, and you have the inverse G rotation here. So basically, these are just basis changes acting on this operation in the center. Okay, and you will spot these all the time in quantum compilation. Like if you can see these in your circuit, you can save massive amounts of time when doing controlled operations, because when you just have a basis change on each side, the only information that you need to control is the single qubit in the center. So naively, you would control every single one of these gates here. Yeah.
Do we need to select a special basis, or does it work any?
Any basis that undoes itself, any operation that undoes itself, and there's something in the middle can exploit this trick.
I mean, for your applications, yeah, in general, it would work with any, but how do you pick for your particular applications which basis is the good one?
It's completely independent. So whenever there's a matrix structure that has this, it doesn't matter what basis it is. So just look for these kind of things in your circuit, because then you can implement very cheap controlled and multi-controlled operations. Okay. Yeah, so we've gone from what would have been 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 controls to single control operations. So you can see why this spotting these is really important in quantum compilation. So this is one of my favorite tricks, actually. So yeah, so you can see now we can then, so this allows us to basically implement this phase estimation algorithm quite fairly cheaply using this trotterization primitive. Now there's obviously other ways to do phase estimation using more complicated time evolution structures like cubitization and etc., which have better complexity. But from an implementation standpoint, I've not seen many people implement cubitization iterates at the circuit level, whereas this is quite easy to do. So if you actually want to, you could do this probably today if you had some time. So yeah. Now, obviously getting the state into this state, which requires the inverse quantum Fourier transform, is a very complicated, very complicated control operation with powers of unitary, so you're going to have really deep circuits. But it turns out there's been you can actually do it a bit more cheaply, and there's been some kind of progress in the past year or two using just simple primitives such as the Hobart test to basically study phase estimation. So the phase information, the eigenvalue information is inside this transition matrix element. Okay. So how do we have to implement transition matrix elements on a quantum computer? Simple bracket operations. The idea is the answer is the Hobart test. So now the Hobart test, to summarize, is basically when you have a controlled unitary, it doesn't have to be an eigenstate as well. It just has to be some state. When we have a Hobart model answer that we controlled unitary and Hobart again, and we do P0 minus P1, this gives us the real part of the unitary expectation value for the input state. Now this is obviously a really, really important primitive, because it allows us to do expectation values, basically. So as this is a tutorial, I will derive this for you, apply as we've seen this before. The first Hobart on the first state, this will take the 0 to the plus state here. So we've got 1 over square root 0 plus 1. And the second state, the second register, which contains the kept state, hasn't changed. And then we do a controlled unitary. Now we should all be familiar with this by now. So we do a 1 controlled U. This is only, the U only acts on the 1, only fires on the 1 state here. Okay, and you can see we now can't factorize this again. So we've got some entanglement going on. Now, you then do you apply Hobart again, and what this does, you can see basically this 0 and this 1 then get rotated again by the Hobart. So you can see each one's got, the 0 has gone 0 plus 1, and the 1 has gone to 0 minus 1. And then obviously because that applies a factor of square root of 2, 1 over square root of 2, we now have a half factor here. And what you basically do is you group the terms from this step. You group all the 0s and group all the 1s, and you get this nice, you get the 0, all the 0 terms here, and you get all the 1 terms here. Okay. Now we have to measure. Now measurement is essentially, it basically gives you that, you can represent measurement as this kind of Born probability, squared probability amplitude. But obviously, if we're just measuring the 0, this 0 here is just going to be 1 because it's, so this yeah. we square the half, that goes to a quarter. And then obviously, we're basically applying the square, modulus squared, to each term in the product. And basically, this zero term cancels, and the half turns into a quarter because it's squared. And then what you're left with is basically the bra side and the ket side of the measurement. Okay. And you can basically multiply this quadratic together, and you get this term. This is an orthogonal basis. That's a 1. This is a u dagger. That's obviously going to be 1. And this will then just become 1 as well. So you end up with kind of these two terms here. Because this is a unitary operator, you basically end up with it's the same. That is basically the real part of this operation. Yeah, when you have two of them, when you add them together, they're joined from there. So yeah, so you basically derive 1 plus the real part of the unitary bracket excitation value. Now, obviously, this isn't the excitation value now, so we actually have to combine this with the minus P1 state. So I would encourage you to derive the P1 excitation values, but basically you end up with this form, where you get basically 1 plus the real minus 1 minus the real. And then obviously this is a minus has a minus, and you get basically plus here. This is why the Hadamard test can derive expectation values for you. So it's a really useful primitive. And this has been applied, and I should say, you can also, if you want to get the imaginary part, all you do is add this S gate onto the ancillary register as well. So what this does, when we apply it to, we can then apply this to kind of our time evolution algorithm, because we can essentially, for different n times, we can basically get the real and imaginary transition matrix elements over time. Now, there's been some nice work in this area to kind of, so this is some work by Lin recently, published this year, actually very recently. And they came up with this brilliant idea where essentially you use the Hadamard test that we showed on the last slide for different values of n. So you basically get this discrete spiral. So this is kind of measuring the spiral of the evolution, right? So you can use clusterization here, and using the controlled cluster, we can obviously implement this operation very easily now, because we can do controlled trotter, like Pauli exponentials really nicely. So when we're using trotterization for time evolution, these Hadamard tests for time evolution actually become very simple, because you're just using this kind of structure. Okay, that's yeah. So you can use these controlled Pauli exponentials to calculate the trotterized form of this time evolution operator. Yeah. Now, what they do is essentially it's a really clever idea, I think. Very nice. So you sample the time evolution as these blue dots here. So like, yeah. And then what you do is essentially, you know this is a complex exponential function propagating in time. It's one of these like messed up spirals. So what they say is, can we just fit a complex exponential function with fixed radius and variable phase gap to the data that we have? So you can say that this is a fixed spiral here, and which only has one kind of frequency and a fixed R, and then we fit this to kind of the real data that we obtained from the Hadamard test. So you can see that you just have this loss function, which is the data from our spiral, the actual Hadamard test data, and then we're fitting this to the kind of fixed exponential here. So yeah, and you can kind of see it, like it makes a lot of sense, right? Like the dominant eigenvalues typically dominate the spiral, basically. So having a single complex exponential makes a lot of sense. Now, what was very interesting that they did is then they showed that because this is an analytical function, you can actually differentiate it by keeping the theta fixed, but minimizing it with respect to r. I encourage you to do this in your free time, but it's just a gist of the algorithm. You then get this kind of this new differential, which you can substitute back in. So you basically end up with this loss function, which minimizes the fitting in this form. Okay. Now you might see this is obviously this Zn is just the data of the Hobart test. So this is the only variable with respect to r and theta on this side. So you just have to maximize this term here with respect to theta and r. Yeah. And basically what that gives you is basically this fitting function here. You maximize this final term, and you basically get this. You differentiate analytically and substitute back in. You end up with this maximization function, because this is a negative here. And basically, you can construct this kind of analytical peaked diagram from this simple idea of a fixed exponential. It's interesting that this actually is just a discrete Fourier transform squared. So there's questions as to whether you need to do this, because it's very related to the discrete Fourier transform. But it's interesting nonetheless that they managed to derive it from this simple complex exponential function. Yeah.
What's your optimism with respect to doing PE-based methods on these devices? Because when I hear
there's a Hoover behind me.
Sorry, I said, what's your optimism with respect to doing PE-based methods on NISQ devices? Because when I hear phase solution, right, I think of really fault tolerant.
Yeah, yeah.
So I'm a bit surprised that these proxies even work at all, right?
So this is it's marketed as a early fault tolerant algorithm, this one. But my argument is that it uses trotterization, and then my colleague showed that it was possible to do trotterization on our current hardware. So that's why I would argue this could be done near term. And there's not been that many successful Hamiltonian simulation algorithms really. So I want to focus on like what's the cutting edge pretty much. Yeah. Anyone? Okay, cool. Okay, yeah. So you basically get this peak structure where the peak corresponds to the eigenvalue, basically, which is this theta. Yeah. Now it's pretty nice. Like you can see that here's an example of the perfect initial eigenvalue for the Hobart test, and then a mixed kind of like a poor guess. Okay, and you can see that you've always got the perfect spiral of just the one frequency corresponding to the eigenvalue of the eigenstate that was the input, and then in the yellow one we've got this mixture of eigenstates. You've got these like competing spirals. So this is the exact one. And you can see this is hydrogen, simple hydrogen example. So the eigenstate, the ground state is -1.13, 1.13. Normal basis hydrogen, 4 qubits. But you can see the peak here is exactly what you'd expect. Now, what is quite surprising in this algorithm is how well it resolves the peaks from the poor input. Okay, so you can see here we've got some overlap of some other eigenstate here, but the dominant peak here is obviously the ground state of is the ground state that we're interested in. Okay, and there's obviously they've also done some work here in kind of when you don't have good overlap, how do you kind of improve that? And you can use some like signal processing techniques to improve it. But yeah, so this is probably one of the best options for phase estimation in a near term, I would say. And it exploits these simple primitives from the Hobart test, which we've shown can be compiled quite efficiently when you're using trotterization. Okay, so now I'm going to kind of change the topic a little bit. It's continuing on use cases of Hamiltonian simulation. Now, one of the kind of if you're a physicist or whatever, and you've got a very complicated problem, the first tool in your toolbox will be to do an exact diagonalization of that system to find the ground state. Now, typically this will be an exponentially scaling basis, right? So the altitude. So yeah, so you have a basis expanding your wave function. Typically this, if you want to think about this in terms of qubits, I could be a bit string. This is going to be exponentially scaling, right? As you get to larger systems. Solving this generalized eigenvalue problem becomes highly intractable. There's a hell of a lot of numerical methods in this area. Most notably the Lanchos matrix vector solution to this. But for the purpose of this demonstration, we're just going to think about pure generalized eigenvalue solution problem. Now, the matrix elements of this H are typically just you have one state, your operator, and then you have another state here, J. And you obviously have exponentially scaling squared number of terms to figure out here, which is really bad. And obviously, if it's a non-orthogonal problem, you've obviously got an overlap matrix to kind of calculate as well. This is all just kind of standard in algebra. Now, one of there's a technique that you can use, it's called Krylov methods. Basically, what Krylov methods do is they apply powers of a function to your ground state, to some initial guess, which then generates a much smaller basis, basically, and then you basically within each power of these functions contains the rest of the basis. It will make sense in a second. So you basically end up with this new basis, which is much smaller, but within each one of these operations contains the rest of the basis. And then you end up with a much smaller eigenvalue problem to solve, which is kind of tractable. Now, what this function is, it's a very elegant algorithm because these functions can be anything which acts on your Hamiltonian. So they can be, so they can be famously kind of, the most used one is kind of imaginary time evolution. This is what the Lanchos algorithm falls down to. You can also use Cheryshev polynomials, which we'll probably hear about later on. But you can also use, you can see for the time evolution operator, the function of h that you're using is just e to the I ht. Okay. So you can exploit the Hamiltonian simulation to do these Krylov matrix problems. And basically, the matrix elements become much smaller. So you're calculating a matrix here, and the matrix here is now made up of these powers of these functions of h acting onto your ground state here. And your overlap matrix is the same. So you're kind of generating a basis from the application of this function of h, and you build the I and j, the basis elements are defined by the power of h that you have, the power of the function of h that you have. Yeah, so in the time evolution, so you can also, there's been some research here, you can do this in the unitary Krylov method, where you can actually exponentiate the Hamiltonian and the eigenvalues. And then when you're generating your basis here, obviously psi of j, which is one of your basis elements, is a function of h indexed by j acting on some initial reference. In the time evolution case, the function is the time evolution operator times by some integer j on time. Now, when you do the unitary, what's very nice when you do the unitary Krylov is that you can essentially, because your operator is now a unitary operator as well, you kind of group together all of these terms, and you kind of get I think it's some polynomial, so some constant linear. Basically, you only have to calculate a constant linear number of overlap elements, because obviously you can kind of contract them more than the one due to the fact that they're exponentials. And also the overlap matrix elements are calculated in a similar fashion. So so there's a nice paper by Katie Kimmicker and Norm Tubman in PRX from last year on this. So I haven't put the reference in. So yeah, and this eigenvalue problem is essentially related to the original Weiss phase. So you can just do some post-processing on it and extract it. And then if you notice, these elements are just the Hadamard test elements that we showed you before. So you can use the Hadamard test with trotulation quite simply at a circuit level to implement these brackets. Okay. So you have a smaller set of these things which could generate a whole eigenvalue problem. So you go from a quadratic scaling problem to a linear scaling problem. yeah, it's a really nice application of time evolution, and it's something that could be done in the near term as well, if you use Hamiltonian test. Okay, for the last half an hour, well, I don't have any questions so far. Yeah.
I have a question about actually quantum phase estimation stuff.
Which part?
Just when we're trying to talk about that, to what degree do actual implementations of that rely on the ability to prepare arbitrary eigenstates of the Hamiltonian? And are there any standardized ways of doing that relatively efficiently?
The answer is this is an open question. So there's a big paper by Garnet Chan discussing whether there is if exponential quantum phantoms exist for quantum chemistry due to the fact that preparation of an eigenstate which has good overlap is very difficult. Okay, so yeah, if I just go back, that's a good question. Actually, I didn't talk about this too much. Yeah, so for the phase estimation algorithm to be successful, in both cases, in the NISQ form and the fault tolerant form, this needs to be as close to the perfect eigenstate that you need. And if you have a bad eigenstate, you can use polynomial number of samples, as long as there is a good overlap. I'm not sure. I think it's more than half with the ground state. You can use a polynomial number of samples to extract the eigenstate. But this is a very hard problem, right? Ground state preparation is a really difficult problem already. So the phase estimation algorithm is kind of hiding the fact that you need to do ground state preparation well beforehand, which is a difficult problem in itself. My favorite method is imaginary time evolution, but this is a non-unitary operation and also is very expensive. So I've got a nice paper on that for the trust relation if anyone's interested. Okay, I'm going to move on to my favorite topic in quantum computing, which is kind of demystifying the linear combination of unitaries circuit primitives. So this is a primitive which is used in many of these fault-tolerant algorithms that you see with these oracular constructions. And it's, for a long time I thought it was just like on this pedestal of a very difficult algorithm that just was compiled down to T-gates and things like that, and used 2RAM and things like that. But it's actually a really simple algorithm when you actually go down to implement it yourself. And I want to show this to you basically because it was very eye-opening for myself. But typically, as we've seen before, the Hamiltonians are weighted sum of Pauli. And in most of these like kind of near-term algorithms, you have to basically measure each Pauli term on its own, right? And then you have to re-prepare the state each time. And you measure this unitary bit, and then you times it by the weighting coefficient. Okay, so it's not very efficient, right? Because you have to re-prepare the state for each Pauli term. Or if you're clever, you can do groupings of Paulis. But the moral is that you have to prepare the state multiple times in this picture when you're measuring Hamiltonians. But what if you could essentially apply the whole Hamiltonian to the state directly? Now, there's a problem here because obviously the Hamiltonians are non-unitary. They're Hermitian typically. Sometimes get anti-dimensional with magnetism. But yeah, if you wanted to implement H to psi, it's quite difficult. It's quite difficult because it's non-unitary, right? And quantum computers are obviously unitary operations. And then also, if you could do this, could you measure the whole Hamiltonian in a single go as well? So you can save all the measurement instructions. And now, I mean, you'll hear about this later on, but if you can do this H acting on psi, this is basically opening the door for all quantum linear algebra. So it's a really powerful property. Yeah, and typically when you have a Hamiltonian which is naturally expressed as a linear combination of unitaries, there's this thing called a block encoding strategy, which uses linear combination. It's called linear combination of unitaries. So yeah, whenever you see these complicated algorithms in papers that are like 50 pages long, just try and break it down to 2 qubits or 3 qubits, and then implement it. It's most of the time you can probably do it. So here's an example of that. So I've chosen the simplest Hamiltonian I could think. This is H equals alpha x minus beta y. And you'll see later on why I've chosen the coefficients to have this constraint here. But if the coefficients have this constraint that the square must equal 1, it means that they can be implemented with this circuit. Okay. Now I'm going to explain this in detail. So what's this circuit doing? Okay, so now we've got an RY here, and if we're using an RY, we can implement this. So if we think about, linear combination of unit trees algorithms have what's known as a prepare register, which is this 0 one here, and you have a state register. Now the prepare register is used to encode the weightings of each of the Hamiltonian coefficients. So you can see here, because our Hamiltonian is, I've lost it, but it's alpha minus beta, and it's obviously constrained to be this. It basically means that we can encode the square root of the coefficient into an RY rotation. And because this is coming in under 0, this only acts on the column, right? So you've got 0, and the 0 state becomes square root of alpha, and the 1 state becomes minus square root of beta here. It'll become clear why we need square roots in a second. So yeah, you can see that on the prepare register, the answer register, we've now encoded the coefficients of the, or square root of the coefficients of the Hamiltonian. Now, you can see once we've got these encoded Hamiltonian coefficients on the prepare, we can selectively apply the power to their corresponding coefficients with these controlled operations here. So you've got a 0 control acting on the x and a 1 control acting on the y. And you can see here x is now acting with, x is now matched up with its coefficient, and y is matched up with the square root of its coefficient. Sorry. And then basically we do this what's called an unprepare, or prepare dagger, which is the reverse rotation. And you can basically see that this multiplies the square roots by its coefficient again, and we get the full coefficient. And now, because we rotate it back onto the computational basis, what this means is we can measure the computational basis state 0, and due to orthogonality, these all go to 1. So you can see that we've now applied this linear combination of unit trees, and due to the linear nature of the operator, we can just group them like this. So this is now applying this linear combination of parallels. So yeah, it's not really that difficult, right, as a primitive. So my argument is that it can be used as a NISQ primitive or a near-term primitive. But don't be scared of it, basically. So in the general case, it's a bit more complicated because you have, you obviously have like an arbitrary sum of parallels weighted by these HAs here, and we have to renormalize the operator by the norm of its coefficient. It'll become clear why that is. But essentially what the LCU is doing is it's this, what's known as a block encoding, which is basically the larger circuit is a unitary, right? All quantum operations need to be a unitary, but basically the post-selection picks you out the block of the larger unitary, which in itself can be Hermitian, right? Or it can be non-unitary. Because the rest of the operator unitary makes up for that, basically. You can see here, this block is indexed by 000 psi, 0001 psi. It's basically a psi for every single bit string on the prepare register. Yeah, so you basically got these psi blocks for each prepare register bit string. Now, in the general case, you have this. Now, it's just a generalization of the simple 2Q example that we saw before. But this is how it's typically shown in the literature. So you have, basically you have this, you start on the 0 state, you have a prepare, which prepares the coefficients, then you selectively apply each of the operators in the parity term, then you unprepare, and then you post-select into the 0 state. Then you apply the renormalized operator. This post-selection has some ramifications, which I'll come on to later, which is basically it has a success probability. But yeah, by post-selecting onto the 0, it puts us into the block, the 000, puts into the 00 psi block here, which is very nice. Now, why do we have to rescale? Basically, because the prepare register is a state preparation step. For it to prepare the state, it needs to obviously be correctly normalized. So you just have to rescale the operators in such a way that the prepare register can prepare those coefficients. And the prepare register scale, in LCU, the prepare register scales logarithmically with, the size of the prepare register scales logarithmically with the number of terms in the operator. because obviously if you've got 8 terms in the operator, you can that can be prepared as three prepared qubits because you've got 2 to the 3 prepared qubits. So this is an arbitrary state preparation problem. I'm not going to go into too much detail about the compilations here. There is still more information in the slides, but yeah, you have to basically solve an arbitrary state preparation problem. The benefit is that because this is a logarithmically scaling state preparation, it's not that expensive as say arbitrary n-qubit state preparation. So this, in the general case, this select operator has this kind of quite scary property, yes.
For the previous slide, like when you post select on these n qubits, the probability of getting the 0, 0, 0 will be like exponentially small.
It's not exponentially small, but there's a derivation for it. And so it also depends on the operator that you're implementing. Like if you have if you're blocking trading imaginary time condition, for example, the longer you go in time, you're decaying to a single state from an exponentially large number of states. So that does have exponentially decaying success probability. Yeah. Okay. So just to finish off the example, so we have this prepare register which has all the coefficients prepared. But what we do is you have to do quite an expensive multi-controlled operation. This is what I've been spending a lot of my time doing, trying to improve the compilation strategies of these things. So you can see we've got this P0, so H0, which is the first coefficient, first Pauli coefficient. And then because this is prepared on the 0, 0, 0 state, we then do this multi-controlled 0, 0 state and apply this Pauli 0 to that 0, 0 state acting on the side. And this P0 can be whatever you want. It can be a Pauli, tensor order Paulis, etc. And we've done some work actually to make this, to generalize this from Paulis to arbitrary SU2 as well, by way of speaking like that. And you can see here, obviously now the second term is indexed on repair by 0, 0, 1, so the multi-controlled select has this multi-controlled 0, 0, 1. And I should say that the 0 controls are these 0 controls are just these white controls are 0 controls. Yeah. Okay. And obviously then you have to do just the prepared dagger of these of the operator, which is basically the reverse of the original state preparation step, and then you can see that we remove the coefficient. So we remove the square root, and we get the correct coefficient, and we just obviously measure now. As exactly the same as before. And we essentially get, because of the orthogonality, these will cancel, and we just get the coefficient acting on the Pauli terms here. So yeah, so you can see this allows us to apply this linear combination of unitaries here. But it's actually, it's not quite the same operation, it's actually this, the operator renormalized by this L1 norm of the operator, which is the sum of the coefficients. Yeah, so coming back to your question about success probability, this is the definition of success probability. So you can see it's a function of the norm of the operator squared, or the inverse squared norm of the operator, and then also the overlap of the application of the operator to the initial state that you have. So it's a function of both the initial state, the weightings of the operator, and the operator itself. But if you can loosely think about this as how unitary your operator is, basically. Yeah. And there's been loads of work in this area for because obviously this H here is just the coefficient of the Hamiltonian. This can be done in the pre-processing step before. This can be modified in the pre-processing step before you can do the circuit implementation of LC. So notable work here is Arthur Ismailov. He's mangling the chemistry Hamiltonians as much as possible to kind of reduce the success probability, improve the success probability without destroying the observable of interest. You can do things like shift the spectrum of the subsymmetry set that you're not interested in, for example, or you may have heard of this famous double factorization, which is a diagonalization of the Coulomb operator, double diagonalization of the double SPD of the Coulomb operator, and then truncation with minimal loss of the operator. Okay, so going back to the Hadamard test, you can actually you can actually, this is kind of what, this is an application of LCU to the Hadamard test. This is something like, this is quite nice. So you can see, before obviously the Hadamard test was limited to just unitary operators. But you can kind of generalize this to Hermitian operators, or anything that you can prepare with the incarnation of unitary this way. So you can kind of now do expectation values of arbitrary operators here. So this is kind of what you would do with NumPy, right? Yeah. So you can use the same idea, and I should say this should be rescaled. Yeah, I apologize. But yeah, so you can basically, it's the same idea as the Hadamard test as before, but now you just basically control this. You control this ULCU, and then you post-select into 0, 0, which basically projects you into the small block of the ULCU. But that controls that small block of the ULCU onto here, and makes act on the state. So it's a bit more instructive if you see. So again, this is why I was saying these similarity transform structures are so useful. Is the fact that you see them everywhere. They crop up in loads of places, and particularly when you're trying to do controlled operations with very complicated things, you can reduce the complexity massively this way. So you can see here we've got this basis, this GUG structure, where the prepares are just this basis rotation and undoing the basis rotation. So, and the select here is the only thing that's like doesn't have this basis rotation. So we can actually use the same trick and just control on the select register here. So like you can think this is a huge saving in terms of qubit compilation because we're not controlling on this prepares here. Now, a large area of my work basically is trying to simplify these oracles. They're often called oracles in literature. It's like these boxes which do things. I think we've got a very unique position now where the circuit simulations, algorithms, on the classical side, are very good now. You can actually get to that. You can simulate quite large primitives. So we can actually start testing these and compiling these primitives. And obviously, like we may not be able to build the whole algorithm, but many of these algorithms are just built from like compositions of these oracles. So a large area of my work is trying to build a compositional approach to these quantum oracles, where we have all the compilation strategies kind of stored inside them. So, yeah. So like you'll see within quantum algorithms, a lot of the recipes are quite similar, like at an abstract level, but it's just the compilations which kind of differ. So yeah. I finished a little bit early. But yeah, okay. That is me. Any questions? Yes.
So I don't know, maybe against Garden and Chan a little bit.
That's nice to hear.
Because I think a lot of chemistry problems that I'm interested in, like say the spectroscopy for astrochemistry, the modern techniques cannot give you spectroscopic accuracy. But the overlap with the ground state and the Hartree-Fock state is like 95%.
Yeah, or higher.
Or higher, yeah. So it seems like there's a lot of chemistry problems where this state preparation isn't an issue. Like what, I mean, that's my opinion. What's your opinion?
Yeah, I mean, I guess the argument is that Hartree-Fock is very efficient classically. Right?
Yeah, but you can't get spectrum.
Yeah, true. Yeah. I mean, yeah, that is it. What spectroscopic accuracy is what 10 to the -7 Hartrees.
Yeah.
That's really what chemists are interested in. It's not this chemical accuracy is kind of the thing that's been invented by quantum computing people. I think. Yeah.
Well,
Yeah, no, I agree. I think, and the point of that paper, I think, is that even if there isn't an exponential quantum advantage, there's still probably polynomial quantum advantage, and no one really knows how to analyze that yet. So there's open work for people interested in complexity theory there. Any more questions? Yes.
How should we be thinking about the role of errors in these types of comparison of circuits you're talking about, right? Because these primitives seem wouldn't we be more concerned about the propagating errors or coherent errors or incoherent errors?
Yes, I mean, so I would say that traumatization. Some of my colleagues have worked in this area where they're not trying to correct the errors, but they're trying to kind of detect them. So you can kind of, the traumatization structures have quite a nice property that they use this code called the iceberg code, which is a detection code. So they can kind of they can't correct the error, but as the algorithm is progressing, they can see if there's an error and just kill that shot, basically.
What code did you say?
It's called the iceberg code.
Iceberg?
My colleague Telluride at Hamiltonian Simulation wrote a paper using Bayesian phase estimation with quantum error detection. So I think quantum error detection is probably this nice medium term circuit, with a way to deal with errors in the medium term, I think. There's obviously error mitigation as well. But, yes.
Hello. I get a little bit confused about the topic and the lecture because I thought it would be like the topic is NISQ, so I think it would be more like considering the noisy qubit something. The lecture we are having today is like we are doing phase estimation. It's more like we need the full tolerant quantum computing something. This is my
I mean, I apologize. My expertise is more in algorithm construction and compilation. So I was trying to give an insight into how you would build the primitives to do kind of some of the successful Hamiltonian simulation algorithms. So my colleagues ran this Hamiltonian simulation algorithm without error mitigation. I guess we're fortunate that we have very good qubits, but it is a near-term algorithm which used the primitives that I explained today. So I think error mitigation and NISQ is it's very hard to see it scaling, in my opinion. So I think if you actually want to write algorithms to do Hamiltonian simulation in near term, it's probably more beneficial to think in terms of traumatization, in my opinion, and the algorithms I presented today. I apologize if I didn't include any error mitigation in the talk.
thank you.
Yeah.
You measure half of the qubits.
Can't hear.
Sorry, you measure half of your qubits in the current Quantinuum algorithm.
How many qubits?
Half of the qubits, like just you described, right?
So I said,
Like when you implement LCUs,
Yeah.
you have to measure only half of your system.
yeah.
And can you do that in your current hardware?
We can do mid-circuit measurement. Yes, I think that's one of the benefits of having this.
Is that available for public or?
Yeah.
Okay.
Yeah, we've got an emulator which can simulate all of these things.
So with numerical linear algebra, you typically want to kind of move bounds on the error. So I guess I'm just curious, do those methods, are they similar when you start to use numerical linear algebra with a quantum computer?
There is a lot of work in this area on kind of complexity analysis for particularly the quantum singular value transform. I'm not an expert in this, I would say, but I mean, we have one of the authors in the audience. And also Linden is very big on this kind of applied maths stuff as well at Berkeley.
Yeah, could you talk a little bit about the problems? You know, you were saying you're coming from the chemistry direction.
Yeah.
So what are the sort of problems that you think sort of near term for computers to solve?
We are genuinely having problems in finding algorithms which aren't already, because classical quantum chemistry is very, very good, right? It's been 50 years of like numerical methods in this area. I think the areas which I'm particularly interested to solve midterm kind of mixed nuclear electron dynamics. So when you have the wave function which corresponds to your nuclei and your electrons in this coupled fashion. So it's like, and I spoke about this before, but like vision in the eye, like that's a cis transatomization of photoexcitation, which causes nuclear dynamics. These kind of problems, I think, are very hard to study classically. I mean, the near term, it's all about finding the Hamiltonian, which is very difficult to solve classically. We don't have the option to be able to tune our Hamiltonians in the same way as, like, for phase transitions, like the Hobart Model, for example. So you have to kind of find the problems which have Hamiltonian coefficients, which are very hard to do classically. I mean, the ones that I think are very nice are kind of problems which have a lot of electronic movement. So like molecular wires, things like that. So things with lots of electronic flocculation and correlation. So things like molecular transistors are quite nice, those kind of things, where you might have like a charge transfer when there's a certain voltage applied to a